va mejor para que...
Okay, good morning to everyone. My name is Andrés, and I will be presenting today the work that we did for my master thesis research under the supervision from the university, from Álvaro Lorca and Rodrigo Barrasco, and also my supervisor from HIF Global, Alexander Tremel. As a way of introducing HIF Global, that is a company that is deeply related to the presentation and the research. HIF Global is a company that manufactures e-fuels. E-fuels are a way to, e-fuels are a way to carry energy. The world is racing to decarbonize, but electrification alone is not enough. Okay, so carbon neutral e-fuels allow the renewable energy to be packed, stored, and transported to world demand centers. And HIF Global is seeking to become the world's largest producer of e-fuels by 2030. We are already producing carbon neutral e-fuels in our pilot plant, demonstration plant in Magallanes, that has a wind energy turbine that turns power into gasoline. Okay, so why e-fuels? Electrification alone is not enough. That's our business case, because as you can see in the graph, we here have in the y-axis the amount of energy per liter, and in the x-axis the amount of energy per kilogram of different energy carriers. As you can see here, the lithium batteries are really close to zero. This means that they have not enough energy density to be a good application for trucking, for example, where weight restrictions are really important because of road restrictions. For aviation, the volume of the energy carrier is also important, and for shipping, the price is the key the key feature that is a driver of the industry. So, for example, liquid hydrogen and compressed hydrogen are really expensive to store and to manage, and they don't make a good business case for the shipping industry. Okay, so our Harwoni pilot plant, it's already working. It's demonstrating that this process can be achieved, that we can turn renewable energy, wind power, into gasoline, into a good energy carrier. The Harwoni facility has a 3.4 megawatt turbine. It's just one wind turbine, and a production capacity of 20.5 green hydrogen kilograms every hour. Okay, this turns into 350 tons of methanol each year. That is, and also we distill 130 cubic meters of gasoline each year. There's a nice photo of Harwoni. It's really south in Chile, where the wind is really strong. Hope you can see it someday, because it's a really nice demonstration plant where all the process is explained. So to the problem that I investigated, the e-fuel plant optimization challenge is the problem we are facing. So in an e-fuel facility, we have here in the left the input power as a sort of way of speaking. We have like a fixed wind park, for example, with a profile that we already know, and we want to know whether we must do a big investment in electrolyzers, for example, with low capacity factor. It's not used all the time, the machine. Or in the other extreme, a small investment with high capacity factor. If we install a little electrolyzer, we can use it most of the time. So and the optimum is somewhere between those two extremes. Okay, for the storage and the synthesis of methanol components, it's the same problem. Okay, we want to know how much of each component we should install, taking into account the capital investments, the operation costs, and also the revenue that they are going to give us. The proper problem statement is the following. Here we have an example process flow of the methanol plant. We have energy that comes into a storage unit. Then the energy, this could be a battery, for example. Then the energy goes to the electrolyzer that makes hydrogen, and that hydrogen goes to the compressors, to a storage unit, or also a tank, and then the methanol synthesizer. And all these components are not have to be designed, have to be sized properly. Okay, so the optimal plant design problem is to determine optimal capacities for all plant components. These are all the components that are encircled in dashed lines to minimize the total annual cost of the system. Okay, so this has been done. This has been done for other industries, for the electrical networks. It's a problem that has already been visited. But there are some specific challenges for the power to X industry that have not been attacked yet. Okay, so some of these challenges are run restrictions, for example, and minimum loads for components, part loads, efficiencies for some transformers. So when you operate at nominal capacity, efficiency is different than when you operate at half capacity, for example. And that the investment scaling is non-complex. This is the one that is most interesting to me, because mathematically we did a good approach to it. So to explain a little bit more about the last one, the investment scaling is quasi-complex. This means that if you install double the capacity of one component, the costs don't scale twice as much, but they scale by a factor with a power of some number between 0 and 1, usually 0.6 or 0.8. So this function that we want to get into the objective function is non-complex, and that's a really big problem, because as you can see here, the optimization methods don't get to the global optimum, but rather to local optimum. Okay, so constraints make the solution initial point dependent, and global optimality is not guaranteed. There are some methods that they are available, and we are going to explore what we did about it. The first that we did looking into this problem was a literature review. So in this table is like the literature capability summary. There are several tools that attack this problem that are designed for different industries. Okay, so most of them are for power networks. Some of them are simulators. Some of them are optimizers. But no one of them attacked all the problems that we want to attack. Okay, so for example, OMOF has this seems that this attack doesn't attack no problem, but actually we base our structure, our mathematical structure on OMOF. But as you can see, there are several ones that attack many of the problems, and FINE is the one that we compare with when we are doing the optimization. Our contribution, our scientific contribution on this thesis is that an optimal plant design model is proposed to determine the parameters of a generic energy system. This means that we can have input to the model several plants, whether we are aiming to make gasoline, methanol, or ammonia, or whatever, or your sources are wind or solar, etc. You can input different things and output different things. Our model addresses every challenge of the previous table that are needed for a power to X plant, and it provides an approach for optimizing the design of e-fuel production plants. The implementation of this model shows significant improvements in computation time over FINE, that is the existing tool that we tried, and proposes a better business case that is validated in an off-sample simulation. How we structured the system, we took this from several tools that also divided it like this. We have in the middle the commodities. Commodities are the materials that have to be balanced. For example, electricity is the obvious one. The electricity that goes in a given moment minus the electricity that goes for all the processes, and taking into account the amount that is stored on each time step should be balanced. So each one of the commodities will translate into a balance equation in the model. The processes here in the left are components that take one or more commodities and produce one or more commodities, okay? The idea of the processes, for example, like methanol synthesis, that is a really complex process, takes CO2 and hydrogen and also electricity and produces raw methanol, okay? The methanol distillation is the same, takes a little amount of electricity and converts raw methanol to distilled methanol. Each one of these processes yields a variable for each time step for how much they are outputting on that moment, okay? In the right side, we have the input and output and storage components. In red, we have the storage. We have, in this case, CO2 storage, batteries, hydrogen storage, and raw methanol storage. The only inputs to this system would be the wind park that provides all the necessary energy to this process. And the outputs are the methanol export, that is the main output that has a price on it, and it's the driver of the model to install more. And the excess electricity. The excess electricity, it's just to give the model freedom to do whatever it wants on every time step and not be constrained to maintain. I mean, if it wants to waste energy, it can do it because it is necessary sometimes. When the batteries are full and the wind park is operating at maximum capacity for several hours, it's necessary. Just a mathematical introduction. This was all translated to sets and indices. This is like the nomenclature of the model. We have set commodities, set of inputs, processes, etc. And here we have the variables that are more important. On the upper part here, the X and the S's are the amount. The X are the flow of commodities for every process on each time step, and the S is the storage level of each storage at each time step. Mu is the only variable, binary variable on this model that tells if a component is on or off, and the N's are the design variables that go to the objective function. So in each time step, X should be always less than N. Okay, so N wants to be minimized because it yields cost, but X wants to be maximized because we want to produce more methane. Okay, those are the variables of the system, and then we have all the parameters necessary to do this optimization. If you want to see them more thoroughly later, we can do it, but I don't think this that relevant. Going into the objective function, what we want to minimize is the total annual cost of the plant. Okay, we have the cost associated with the inputs installation. We have the capex, that is the installation cost of the component, multiplied by the annuity factor and the operation and maintenance factor, that are the factors that make this an annuity and not just an upfront cost, multiplied by the NI variable, that is the one that tells us how much of this input we installed. The same is for storage, and for the processes are kind of the same, but the N goes to the power of this gamma number, that is the number that I was talking about, that is between 0.6, 0.8, depending on the components. We also have the input cost. For example, if we want to purchase CO2 at a given price, or we want to connect to the grid electricity that has variable prices over the day, we can also put that in the model, and minus the outputs, the revenue given by outputs. This, for example, in this case, we fixed a price for the methanol, and we sell it. And that translates into a minus sign on the objective function. We could also have a PPA contract with for electricity to give out to the grid. Also, it would give us revenue, and we can also put startup costs on this objective function for when starting a component has a cost. Okay. The constraints of the model, I will just touch them from above. The commodity balance, was the balance that I was talking about, takes into account the inputs, the outputs that are linked to that commodity, and the processes. The processes is a big factor because it's a really complicated factor because we take into account the different efficiencies when operating at 2 points. Okay, this is a linear approximation. We have a point on the nominal capacity and a different point, and we do a linear approximation on those 2 points. And also the storage is what comes in, what comes out of the storage. It's also balanced. Then we have the storage balance, the same. The storage level at one time step has to be the balanced of what we had in the previous time step plus what entered minus what got out. The capacities are here on the bottom left, and is what I was telling you earlier. The x must be always less or equal than the n. Okay, so the n wants to be minimized, the x wants to be maximized. The process ramp rates are out there, up right. And they tell the components that they cannot change their operation rate that fast. They must be bounded by some amount every hour. Okay. The process minimum loads enforces that the mu variable is 1 whenever it needs to be 1, as well with the startup costs to ensure that the variable takes into account all the starts of the components. Also, we have minimum downtimes and uptimes. This is not a really realistic approach, but it's mathematically equivalent to what we would do in reality. Okay, so if you don't have enough power to drive a complex component that like methanol synthesis, you have to turn it off, and then the process of turning it back on is really costly in time. So the model understand that if it turns off a component, it must have it off for a long period of time, that it's ensured by this tau down parameter. About the non-convex scaling, the approach that we took is to do a piecewise linear approximation. As you can see here, the blue line is the real cost, what it would cost the actual components, and the standard approximation for all the literature tools that we reviewed is the green line. Is to fixed. It's just a cost that scales with the amount of installation linearly, and as you can see here, for big capacities, it's not a good approach. So what we did was divide this range into n parts, n varying. We use 10, but we could use 200 if we wanted to be more accurate. And we did this approach by the orange line, that is the one that the model uses. The interesting part of this approximation is that it only adds 10 binary variables to the model. and not and not 10 every time step. That would be a problem, but it's just 10 or just 200 if you want. That it's still a low number for the optimization for the model size. This is the equations that model this approach, and they actually did a really good job finding the optimal case. Okay, so this model was implemented on a case study, on a theoretical exercise that is near a real case. We have technical parameters for electrolyzer, compression, direct air capture, methanol synthesis, and distillation. That was the components that we installed that have efficiencies, ramp rates, and minimum loads. And we have here in the bottom table the cost of these components, the investment cost, and also the operation and maintenance cost for all these units. We have with the wind park, electrolyzer, direct air capture, methanol synthesis and distillation, and also storage of different types. We have a battery electric storage system with capacity and power costs, and then hydrogen storage, CO2 storage, and raw methanol storage. The first experiment that we did was to compare the computation time of our tool against the other tool that we used, that was Fine. We choose Fine because it has the most capabilities of all the other tools. And here in the left is the comparison between us and Fine, between PDXG and Fine. As you can see, in the x-axis we have the size of the model, and in the y-axis the computing time that it took. As you can see here in the logarithmic scale, the orange line scales with an exponent of almost 2, and the blue line with an exponent of more than 3, and it gets really high very fast. As a matter of fact, we couldn't do the next point on this line because every optimization took more than 48 hours to do. I cut it off at 48 hours because I didn't thought that it was relevant if we were optimizing 60 days to have that much of an optimization time. So as you can see here on the left, we are far better than the tool that we compared with. Then on the middle part, it's a comparison of our own model working on different ways. The green line, it's when it's purely linear. We don't have components with minimum loads, so there are no binary variables, and it's the lowest time of it all. Obviously, because it's way more faster to solve a linear problem. And the two other lines was the linear approach. The green line that I was talking about earlier. This one. So one is the linear approach, this here, and the other one is the non-convex approximation that we did. We wanted to measure how much of a difference does that, and as you can see here, it does not make a significant difference between the orange and the blue line. Are really close together. So there's not, as expected, there's not really a great difference between the two models. On the right, we have the comparison between CBC and Gurobi. That were the two solvers that we used. This is programmed using Payomo, that is solver neutral, if you want. It can use Gurobi, CBC, or other solvers, open source solvers that are out there. As you can see here, the dashed lines are Gurobi and are way faster than CBC. And they are two lines for each one because this is the linear approximation, and then the non-convex one, the full model. Also for CBC, we have the linear and the non-convex model that are 2 orders of magnitude higher than our approach. That was the first experiment. The second experiment, and the most interesting one, I think, is the optimal design. The optimal design that is the output of the model, is how much of each component should I build. So first, if we look at Fine, that is the tool that we compared with, Fine, the largest amount of time that it could take was 30 days. So we did also a 30-day run for PDXD. And for Fine, we took the best case scenario. Of all those 30-day windows, we took the best one, the best business case, and compared it with the median case for PDXD. As you can see, the electrolyzer capacity installed, it's really low for Fine. It prefers to do a small investment and to operate it at a high capacity factor. And but PDXD installed 10 times that and operated at a low capacity factor. Also, Fine didn't install any storage for this plant, but PDXD installed several ones. As you can see, the electricity loss, the electricity that is lost in the system is almost 2,000 gigawatt hours every year for Fine, but for PDXD it's just 20. The total income is $23 million for Fine and 135 for PDXD. And also, that was like the first experiment. It's really different between Fine and PDXD with the results. And the second one is between the 30 days optimization and the full year optimization for PDXD. That is the red column in the middle and the red column in the right. As you can see here, the component sizes are somewhat similar, 267, 266, for all the rest of the components as well. But the hydrogen storage capacity and all the other storage are really sized differently. You have 12 tons of storage for the 30 days and 41 tons of storage for the full year. And that's expected because if you have a full year, it makes more sense to invest on a larger unit, larger storage unit. Okay, the electricity loss is somewhat the same, and the total income is a little bit greater for the full year case. How much it installed between the linear approximation and the non-convex approximation? It installed somewhat the same, like the red line is with the linear approximation and the blue line with the non-convex one. It is almost the same, and this is because the methanol synthesis and distillation were the only components that were affected by this non-convex approximation, and they were not as expensive as the electrolyzer, for example. So if the size of these components was really driven by the price of the electrolyzer. So the model first does the electrolyzer installation and then decides how much of methanol synthesis and distillation to install, because it has a low cost. If we would implement non-convex scaling for other components, probably the difference would be greater. The optimal operation, that is like a really interesting figure. We have here the power generation of the system that has in blue what the wind park inputs to the system, and in orange what the battery inputs to the system. And here is the power consumption of the different components. As you can see, the battery kicks in whenever it's needed to keep running the methanol synthesis, that is the component that never turns off. Also here in the bottom, we have the storage levels for this system. As you can see, the blue line and the orange line, there are the battery and the hydrogen storage, cycle a lot of times in just a week. And that is interesting because we have no more than 48 hours of storage of hydrogen or electricity. But the raw methanol storage, for example, or the CO2 storage are more seasonal. They have like 30 days of a supply to use in the components. We have also a winter week. As you can see here in the winter, the CO2 amount that is stored is really low. Okay, so the problem that we have now is that the model knows the future. The model knows the future, and that's why it can output an optimal operation. So what we did, we are here. We know the present, past, and future. We did an optimization, and we have an optimal design with a perfect operation that knows everything. So we want to know how attainable is this this operation just by a simulation, something that knows the past, the present, and no more. So we, for this case, did constructed a simulator that takes this perfect operation and an operation that we propose and compare between them. So we should know with this approach if we need a dynamic optimizer to do the optimization on the plant. And the results are really great because we do not need for this plant a dynamic optimizer. We did a simulation for an off-sample year for 2014. The optimization was done for 2019, and then we took those design values and plugged it into a plant from 2014, and the results are really great. As you can see here in PTXD, the most on the right, the red column on the right, the electrolyzer capacity factor was 58% for the optimal operation of 2019 and was 61% on the simulation on 2014. It's higher because the wind is higher on 2014, but it's in the same order of magnitude, even better. Okay, the total income is $144 million a year compared with 138 for the optimization. Also, we can see comparing Fine and PTXD that Fine performed really poorly because this 99.5% of capacity factor that Fine supposedly attained is not attainable without storage. Without storage, you cannot attain this 99%, and that's why it has a 33% capacity factor that is really low. What's the output of the master of this work? I did an I-Force presentation in the I-Force conference in July this year. I also presented in this seminary a couple of weeks ago, and we submitted a paper to Sustainable Energy Grids and Networks journal. And also, and I think the most important is that the PDXD model is being adopted by HIF Global's innovation team, and it's going to be used on the industry. As a way of summarizing, a mixed integer linear programming model was proposed for a generic Power-to-X plant that addresses all proposed challenge for this industry. The model optimized a theoretical case that it's near our project in Patagonia, and we showed that purpose-specific modeling improves a lot on computational time and overall economic convenience. The resulting designs were also validated with an off-sample simulation. The next steps for the model are the dynamic optimization. We have to do a dynamic optimization model for more complex plants that may be needed, and to apply this to a system that has non-convex scalings for more than one component and also for storages. Next steps for me, I'll use and further develop this model as part of the HIF EMEA innovation team in Berlin, Germany. I'll be a developer engineer trusted with regional project support from an optimization point of view for all the regional projects of GIFGLO. Thank you very much.
Excellent, Andrés. Do you hear me well?
Yes.
Excellent, excellent. So thank you very much. Very clear, good in the timing. So now we